Yes, sir.
So it's all based on the request from students. And I hope all the students who asked for the doubts have read the topics and come prepared to find any deficits in the presentation or discussion. Correct, Soundarya?
Yes, sir.
Right.
Yes.
Supriya madam has joined. Shall we go ahead?
Yes, sir. Yes, sir.
Okay. So first, what shall we discuss? Sodium or oxygen or CPB?
Sodium.
Sodium. Okay. So sodium was Soundarya's request.
Yes, sir.
Okay. Right.
Yes, sir.
So
Thank you.
all of you know a lot of things about electrolytes and electrolyte imbalance. And so instead of a didactic lecture on that, I have again made it into an interactive session by asking a few questions, or the whole PPT has been prepared as a question and answer type. So the questions will appear. You can answer whatever you know. If it is not correct, we will try to correct it by showing the answers.
Yes, sir.
Okay, shall we go ahead?
Yes. Yes, sir. Yes, sir. That's one.
So sodium homeostasis and imbalance is a very important topic. And so how much is the total body sodium? How much of sodium we have in our body totally?
Around 140, sir.
Around
140. 140
40 what units? Milligram per liter or milligram per deciliter or total?
Milliequivalents per liter.
milligrams per liter.
Milliequivalent. That is the value
Total.
that in the extracellular fluid. Is it to be declared in milliequivalent or milligrams percent? Milligrams per this thing?
Millimole per liter, sir.
When we eat, what is the main source of sodium for us?
Salt.
Dietary sodium, isn't it?
Right.
So we add salt to every food that we. So main source of sodium is dietary sodium. We take it from the diet. Okay. So
Yes.
it is total pool of sodium in the body is supposed to be 4,200 millimoles, which is roughly 60 more per kg, which is our average calculation. We always take 70 kg as a normal adult value. Okay. So this is the total pool of sodium in the body. How is it distributed and in what manner is distributed? How is the sodium distributed mainly? Is it an extracellular element or an intracellular element?
Extracellular.
Extracellular. So it is mainly an extracellular. Okay. So 30% of it is non-exchangeable. Out of this 4,200 millimoles of sodium in the body, 30% remains fixed in one compartment. And the rest of the 70% is only in an exchangeable form. Out of that, 15% is in the bone, 10% in connective tissue, 45% dissolved in fluid. Okay?
Yes,
So
sir.
in body fluids, what are all the locations? So 45% which is dissolved in fluids, how is it distributed? It is distributed 30% in interstitial fluid, 10% in plasma, and 2.5% as transcellular fluid and 2.5% as intracellular. Okay? So the intracellular portion is very, very low. As you all know, sodium is mainly an intracellular electrolyte ion and potassium is the main intracellular ion. So these are the locations where it is situated or distributed in the body fluids in the extracellular space. Now, what is Gibbs-Donon effect? Unless you understand this particular effect well, you cannot understand why sodium is mainly extracellular and what is its effects on the various systems. Have you heard of this effect, Gibbs-Donon
Yes, sir.
effect?
Yes, sir.
What does it say? Whoever said yes, you should at least mention what is the concept behind this effect. You are not sure about it, say no, I'll go ahead and complete the answer. Okay?
No, sir.
No, sir.
Not very confident in.
Yes, sir.
Yes, okay. So the Gibbs-Donon effect, also known as similarly Donon effect or Donon law, it is the behavior of charged particles. All of you know that all the electrolytes in the body are charged particles. They always carry a positive charge or a negative charge. And they are, when they go to the permeable membrane, they fail to distribute evenly across the two sides of the membrane. As you rightly know that some charged electrons or ions or electrons like sodium is a positively charged. We always write Na plus. Potassium, what is the charge?
Positive.
Can you write what is the symbol of potassium? How do you write the symbol of
K
potassium?
K plus. K plus.
K positive. Right. Chloride, negative.
Cl
Cl minus.
Negative.
Bicarbonate,
CO3
so
minus.
we know that some are positively charged particles, some are negatively charged particles, but they are not evenly distributed on both sides. Why it is so? For example, if you take sodium, it is not 70 milliequivalents outside and 70 milliequivalents inside. It is 140 milliequivalents outside and only 7 to 10 milliequivalents inside. Similarly, potassium is very high inside, 140 milliequivalents inside the cell, but 3 to 5 milliequivalents outside the cell. Why this distribution is uneven? What is the purpose? Why nature has made it that you should have some ions, even though they are positively charged, get distributed in a higher value outside the cell and a smaller value inside, like your sodium, or the vice versa for your potassium, and chloride also, mainly an extracellular ion, very small quantity inside the cell. This distribution is mainly to maintain what?
membrane potential.
Resting of brain potential.
Electroneutrality and membrane potential. Very good. So it is the main purpose is to maintain electroneutrality and membrane potential. Okay. So how does this Gibbs-Donon effect apply to sodium? If you understand this, you will understand that. That is, anionic plasma proteins attract sodium into the plasma. So sodium being a positively charged ion, it is attracted by the plasma proteins which have a negative charge. So it is carried. You don't have a protein inside the cell, isn't it? You have all the more proteins mainly in the plasma. So the negative charge of the plasma attracts the positive charge of sodium and try to retain them in the plasma, number one. So equilibrium reached when the sodium concentration in the plasma remains slightly higher and the chloride concentration in the plasma slightly lower. So chloride ends up being higher in the interstitial fluid rather than in the plasma compartment. And the coefficient which describes this distribution is the same for all monovalent cations. That is, ones which have a single positive charge, and is approximately 0.9%, 95% for sodium compared to the interstitial fluid. Okay. Now that you know why sodium is being retained outside the cell in the extracellular space, we should know why this happens. Mainly because the mechanism we have understood. because it is attracted by the plasma, and also it is attached to some extent, the negatively charged chloride ions. So it is mainly in the extracellular space. And why nature has made it that sodium should remain in the extracellular compartment? The reason, already one reason is given here. That is, it is attached to the negatively charged plasma proteins. And that is the reason why it remains in the extracellular phase. Can you think of any other reason? Is the cell membranes permeable to sodium easily?
No, sir.
No, very good. So when they are impermeable, sodium somehow tries to go in. When there is an action potential, there is a sodium channel opening up, and sodium enters through the stimulation. But how is this sodium pushed back from the intracellular compartment to the extracellular compartment?
Sodium potassium ATPase.
ATPase pumps, okay? And how do they exchange the sodium to the potassium?
For every 3 sodium that goes out, 2 potassium gets inside.
So the number of potassium sodium extruded out is more than the potassium, isn't it? So that is another reason why sodium is mainly an extracellular compartment element. So sodium is not so permeable to cell membranes, are not so permeable to sodium, and the sodium potassium ATPase pumps exchange 3 sodium for 2 potassium ions. So more number of sodium will be extruded out, and the sodium is maintained to maintain the membrane potential at a positive charge outside. So these are the reasons why sodium is mainly a extracellular compartment ion. Okay. Now what equal to this Gibbs-Donon concept or effect? We should also know what is called the plasma solids effect and its significance. Have you heard of this particular concept?
No, sir.
No, sir.
No. Okay. So plasma is composed of 93% of water and only 7% of solid substances. That is the composition of plasma. So when plasma sodium is measured, the concentration is not much different than the interstitial fluid concentration. Okay? But there is actually more sodium in the plasma that is attracted by the Gibbs-Donon effect of all anionic plasma proteins. And if you take the concentration of sodium in comparison to the water content of plasma, the sodium content of plasma water alone would be substantially higher concentration. Okay? And this is known, this discrepancy between the sodium measured by the ABG machine and that is measured typically in the laboratory analyzer. So when you send a sample, venous sample, for measuring the electrolytes, the value you get will not be the same as it is measured by the ABG machine, which is calculated more from the blood gases rather than by the actual analysis. Okay. So this plasma solid effects makes the importance of knowledge that sodium measured by ABG will not be equal to sodium measured with a venous sample in the laboratory when you send the test for electrolytes alone. And this is very important because when you nowadays, after whenever you send a arterial blood sample, you get all the electrolytes also coming along with that report. So that report will not actually be the same as you send a sample purely for electrolyte. So that is because of the plasma solid effects, which will dilute and give a comparatively lesser reading of sodium when you compare to the actual measurement of sodium in the laboratory. So the value that you may get, which may show a hypo or hypernatremia in ABG, may not be completely true. That is the main important message that you have to remember. Okay. Now, how is the sodium intake, which we normally take through our diet, regulated? From which part of your intestines or the gastrointestinal tract the sodium gets into the body? which are the locations of the gastrointestinal tract from where the sodium is absorbed, and what factors help in the absorption. Is there any regulatory mechanism to prevent excess intake and getting into a state of increased sodium level, or all the sodium that you take, will it get absorbed? What is the mechanism? Okay, right. Dietary intake is about 50 to 100 millimoles per day, and aldosterone regulates the colonic absorption of the sodium that we take by oral route to some minor extent. But it is also involved, there is a so glucose couple, that is glucose sodium exchanger or sodium hydrogen exchanger, which we normally find only in the, or learnt about them in the, which particular system with these enzymes are more important or proteins are more important.
Kidneys.
Kidney. So we have been studying only the kidneys are having these exchanges and the proteins to regulate the sodium intake, but here they are present in the intestine also. So they account for the intestinal absorption. So aldosterone, which is mainly acting on the kidney, also acts to some extent in the absorption at the colonic level, large bowel level. And the glucose coupled, that is sodium glucose transporters, which we are nowadays using as an anti-diabetic agent, is also present in the intestine for regulating the absorption of sodium. And 3 millimole out of this 50 to 100 we take is excreted in the stools. Okay? The rest only is absorbed. So how is the intracellular extracellular balance of sodium done? The answer already given in the earlier slide.
Sodium, potassium, ATP.
Sodium, potassium, ATPase pump. Okay, so cellular membrane has very poor sodium permeability. They don't allow the sodium to come in unless a stimulus is given. That is, you go beyond the action, the resting membrane potential, then you reach the action potential, then only the sodium channels can open and sodium will go. But normally, potassium can, to some extent, migrate in and out much more easily compared to sodium. So sodium is very poorly permitted, and sodium potassium ATPase maintains the high extracellular and low intracellular by the exchange of 3 sodium ions to 2 sodium potassium ions. Where is sodium sequestrated and what is its role? Is there any place in our body where the sodium is just dumped in? Sequestrated means it is dumped in, which is not active. Any parts or any location in our body where it is sequestrated? Okay, it is bound to negatively charged residues of glycosaminoglycans in the skin and connective tissue. So wherever there is a negatively charged particle, sodium being a positively charged ion will get attached to that. So to some extent, the negatively charged glycosaminoglycans in the skin and connective tissue will also attract and keep the sodium bound to them. But they are not osmotically active because they are not in a water medium. They are inside the connective tissue and skin locations. They are not osmotically active. Okay? And it serves as a buffer to prevent hemodynamic changes from dietary sodium fluctuation. So if, for example, you fast on a particular day, don't take any salt containing food at all, and that day your body should not become hyponatremic. So the buffering action of this sodium, which is already bound and kept as a reservoir or a store, just like you can imagine the glycogen being stored in the liver, and whenever you fast, you don't have enough glucose. The glycogen is broken down and glucose is given. So in the similar way, sodium is attached to this glycosaminoglycans as a buffer, and if your sodium intake is poor, then it will release the sodium to maintain your normal dietary, blood levels of sodium. Okay. So what is the role of kidney in sodium homeostasis? That is the most important knowledge that we should have. Once you understand this particular concept, how kidneys act on the sodium, then understanding the imbalance of sodium will be quite easy.
Activate the renin angiotensin raw systems, sir.
First of all, when you say kidney, you must say about the filtration. So how much of sodium is filtered, where it is filtered, where it is reabsorbed, is it secreted back into the urine, or is it all only absorption that is taking place? These are the things which you should say mainly in the action of the nephrons, isn't it?
Yes, sir.
So plasma gets 180 liters of plasma is being filtered every day, isn't it?
Yes,
That
yes.
is your basic knowledge that has been taught in your physiology. So 99% of the sodium ions which are passing through glomerulus are reabsorbed. Reabsorbed mainly from which area?
Proximal convoluted tubule.
Which part of the
and
nephron reabsorbs sodium maximum?
Proximal convoluted tubule.
Proximal convoluted tubule. Okay. So the proximal convoluted tubule absorbs 65% of your filtered sodium. Okay, and that the cells are the proteins which help in the reabsorption of apical sodium amino acid co-transporter, sodium hydrogen antiporter, and paracellular reabsorption between the cells of the proximal convoluted tubule. Okay, so there are three methods by which the sodium is reabsorbed after it is filtered by the glomerulus, the Bowman's capsule, and enters the proximal convoluted tubule. These three mechanisms help in the reabsorption of almost 65% of the sodium that has been filtered back into the blood. Then at the level of descending thin loop of the loop of Henle, there is no absorption at all. Whereas as the plasma fluid, filtered plasma goes through the thick ascending loop of Henle, another 20% of the sodium is reabsorbed, and that is done by the other proteins called apical cell. That is, the apical means apical side of the lining cells of the loop of Henle, where sodium potassium 2-chloride co-transporter. This is the protein which helps in the reabsorption of your 20% of sodium at the loop of Henle level. Then the distal convoluted tubule level, there is another protein called sodium chloride exchanger or co-transporter, which helps in absorption of another 10%. And collecting ducts help in the absorption of another 4%. And so 65 plus 25, 85 plus 10, 95 plus 4, 99. So 99% of the sodium is reabsorbed at 4 levels: proximal convoluted tubule maximum 65, thick ascending loop 20%, DCT 10%, and collecting ducts 4%. And at the collecting duct level, it is the epithelial sodium chloride channels. Apical ENAC stands for epithelial sodium channels, which are just small channels which open up to collect the sodium. So this picture tells you about the these 4 things that are happening, and other regulatory proteins or factors which can act on this particular level. So the glomerular filtrate, when it goes into, these are all situated in the cortical level of the kidney. Okay? The proximal convoluted tubule is also situated in the cortex. Then starting from the descending loop, thin descending loop of Henle, it goes into the medulla, and it turns as a U and then comes up and starts as the thick ascending loop at the level of the outer medulla, and then continues as the thick ascending loop, then goes into the distal convoluted tubule and collecting ducts, which again come back to the cortical level. So this distinction is very, very important. The kidney is divided into the cortical portion and the medullary portion, and the medullary portion is again divided into outer medulla and inner medulla. Okay, why this loop of Henle is mainly situated in the medullary region? What is the purpose? This is basic renal
Counter current.
physiology. The concentration, counter current mechanism and counter multiplication, which is the main helping process for concentrating your urine. Okay, so that is the reason why it goes into the medulla, and then again it goes back into the cortex, and then comes down as the collecting ducts, and then the urine is passed out again through the medulla, joining the papillae, and then the major delivery tubes like the pelvis and the ureter start. Okay, so at the various levels, the importance of this sodium delivery at the distal convoluted tubule. What is the purpose of this? Why sodium has to come up? Why not the body make it in such a way that the entire 99% be absorbed at the proximal convoluted tubule itself? Why it should allow the 20% to come up to the thick ascending loop and 10% to the distal loop? What is the importance of that? Now, if this picture tells you that there is a close proximity between the distal convoluted tubule and the glomerular afferent and efferent vessels. Now, so looking at this picture, can you find out or tell me what is the reason for these two structures being situated so closely in the nephron disposition?
Renin-angiotensin-aldosterone system.
Fantastic. That is the juxtaglomerular apparatus. Renin-angiotensin mechanism is the main mechanism to control your vascular tone, isn't it? Ultimately, the angiotensin 2 is the one which is going to control your vascular tone. So when you are in hypovolemia or in hyponatremia, this particular location of juxtaglomerular apparatus is one which is going to stimulate the production of this renin. Renin is a protein which is delivered at the glomerular capillary level, and this protein will go to the liver, and then I act on the liver to convert this angiotensinogen into another peptide called angiotensin 1. This angiotensin 1 has to go to the lung to get converted to angiotensin 2, which is the ultimate peptide which can cause vasoconstriction. So the protein which is secreted by the glomerular capillaries travel to the liver to convert the multiple peptide called angiotensinogen, cleave them, make them smaller, and convert it into angiotensin 1. And this angiotensin 1 has to travel to the lung, get converted by another enzyme called angiotensin converting enzyme, and then become angiotensin 2, which will have the normal effect. For this reason only, sodium concentration in the DCT is very, very important regulator of renin-angiotensin aldosterone mechanism. So whenever your body sodium level is low, the amount of sodium reaching the distal convoluted tubule will also be low, because the filtered volume will, the concentration will be low. So when it comes below to some extent, immediately the body will sense that you are lacking in sodium, and to maintain the volume inside your vascular compartment, this renin-angiotensin mechanism will be activated, and vasoconstriction will happen, so that you don't go into hypotension because of hypovolemia. So that is the main reason for this particular action to come on. Okay, and this aldosterone, it acts on the reabsorption of mainly potassium, but also to some extent it acts on the epithelial sodium channels and maintain the reabsorption of sodium and excretion of maintain the sodium level to some extent. So all these things happen at the kidney level. So remember these 4 levels where sodium is absorbed: PCT, thick ascending loop of Henle; DCT, collecting dip, and the percentage gradually decreases from 65, 20, 10, and 4. So easy to remember. Okay. So what stimulates the sympathetic activity and how is it done? What factors cause a stimulation of your sympathetic system in the body?
Physical
Apart
stress,
from your fear and anxiety, what other physiological factors can stimulate your sympathetic system?
surgical
What do you-
stress,
Huh?
surgical stress,
Surgical stress, okay. Normal physiology.
hypertension,
Hypotension, okay. Hypotension detected by baroreceptors in the carotid and aortic arch, and hypovolemia. Okay, these are all the two important stimuli for your stimulation of sympathetic activity. Hypotension detected by baroreceptors in the carotid and aortic arch, and hypovolemia caused by reduced distension of atrial myocytes stimulate the activation of sympathetic nervous system. What are the effects of renal sympathetic activation? When the sympathetic supply to the kidney is stimulated or activated, what will be the effect? Will it cause afferent vasoconstriction or efferent vasoconstriction or afferent vasodilatation of the capillaries going to the glomeruli? What is the peculiarity of the capillary system in the glomeruli compared to the capillary circulation elsewhere in the body?
Endocrine.
Huh? In other parts of the body, which is the afferent supply to the capillary circulation and which is the efferent part of the circulation? Kamachi, it is showing it will end in 5 minutes. Kamachi, are you there? It shows meeting will end in 5 minutes.
Yes, sir. Again, I'm getting the same trouble, sir. That time,
Okay.
I'll
Will it
create
have a
another link
problem
and send
again?
it now itself, sir. I'll create
Okay.
another link and send it right now, sir.
Okay. Effects of renal sympathetic activity causes increased reabsorption of sodium at the proximal convoluted tubule, which is the activation of alpha 1 and alpha 2 adrenal receptors. Okay. So that is what will happen with renal sympathetic activation. The increase in fluid retention, thereby increasing intravascular volume, blood pressure will be maintained with normal effect. What is the role of renin-angiotensin-aldosterone system activation? That all of you should know that reduced renal perfusion or reduced sodium delivery to the nephron, especially to the juxtaglomerular apparatus, stimulates renin release from granular cells of the juxtaglomerular apparatus, and renin release leads to production of angiotensin II, which stimulates aldosterone secretion, and sodium balance is increased by sodium reabsorption at the nephron. Angiotensin II stimulates the sodium hydrogen antiporter in the PCT, and aldosterone increases the expression of epithelial sodium channels in the collecting duct. So these are all the changes that happen to RASS system. Now, what is the role of atrial natriuretic peptide and the brain natriuretic peptide? How do they act?
atrial volume
By
sensor,
They are secreted by atrial myocytes. Okay, raised blood volume causes increase in venous return and stretches the atrial myocytes. This stimulates myocytes to release ANP and BNP. Okay, so it is a mainly secretion by the atrial cardiac cells, and this hormone promotes natriuresis in order to reduce the circulating volume, because the volume is now seem to be increasing. So ANP and BNP act to reduce aldosterone secretion from the adrenal gland and also suppress the renin secretion from the juxtaglomerular apparatus, thereby decrease sodium reabsorption from DCT and the collecting duct. They also increase glomerular filtration by dilating afferent glomerular arterioles and constricting the efferent glomerular arteriole, increasing the glomerular blood flow. So more filtration will occur. So they will help mainly in reducing the sodium in the blood. That's why they call natriuretic peptides. Okay, so they cause more excretion of sodium in the urine. Okay. Now, having understood that, the next important hormone we should know is ADH, antidiuretic hormone. How is it released? How does it work? What causes release of ADH? What change in the blood causes the release of ADH? Giving more and more clues.
Change in osmolality.
Plasma osmolality, fantastic. That is the main answer. No, the increase in plasma osmolality, where due to dehydration, the plasma osmolality will increase. Blood will become hyperosmolar. It is detected by the osmoreceptors in the thalamus, which stimulate thirst as well as release of ADH from the posterior pituitary. Okay, so there will be a significant effective circulating volume detected by baroreceptors, which also stimulate ADH. So it is primarily because of plasma osmolality stimulating the ADH from the posterior pituitary after being sensed at the thalamic level. Whereas the second effect is the reducing effect of circulating volume. The baroreceptors, which get stretched when there is increasing volume, are able to detect the decrease in circulating volume also. They also stimulate ADH because they want to retain the fluid in the body. So antidiuretic